Good evening, and welcome back to the Kraw lecture series. I'm Raphael Kraw. I think everybody attending this lecture is aware that artificial intelligence has crept into our daily lives, and the subject seems to get bigger every day. If you have ever given a voice command to any of your devices, you have used deep learning. And tonight's speaker will share with us how we can use the human brain as a model to engineer more efficient systems that respond to ever-changing environments. Before we get started, I'd like to welcome back to the Kraw lecture Alexander Wolf, who has served as the Dean of the Baskin School of Engineering since 2016, and who is himself a distinguished professor of computer science and engineering. Please welcome Dean Alex Wolf.
Thank you, Rafe. It's a pleasure to welcome you tonight. Just want to point out that although we are UC Santa Cruz, we actually occupy part of this building as Baskin Engineering. We have 8 faculty and 30 PhD students right here in Santa Clara, and they work on a variety of topics, including quite a bit of artificial intelligence, as it turns out. So it's actually makes a lot of sense for us to be talking about artificial intelligence tonight in this venue. So our speaker tonight is someone who I'm very, very pleased to introduce. He is one of our new assistant professors who's making a name for both himself and for us, which I'm very thankful. Jason is coming to us from Australia, where he has a background in electrical engineering and the law, which I think is not only an interesting combination, but an incredibly relevant combination, given some of the controversies, I would say, around artificial intelligence and its impacts and potential impacts on our society. Jason has a very deep interest in how the human brain works. And when most people do that, they do that from a purely biological point of view or a developmental point of view. Jason is looking at it from an inspirational point of view and trying to see whether there are ways in which computing devices can be made to operate in a way that takes advantage of the best properties of the human brain, you might say. And in that sense, it's an inspiration, not an imitation, but rather an inspiration. So Jason focuses on brain-inspired hardware in particular, and algorithms that take advantage of that hardware. He's drawing on principles of neuroscience, of course, which is the science of understanding the brain, to leverage the efficiency of natural intelligence into artificial intelligence. And as Jason says, hopefully not stupid or stupidity. After joining us only last year, Jason has already launched the Neuromorphic Computing Research Group to explore the many ways brain-inspired technology can be used to solve modern technical challenges and stretch the limits of silicon chips. He's released Spike GPT, which is the largest language-generating spiking neural network to date. And as we do in Baskin Engineering, we're strong believers in open source, and Jason has put into open source the code for Spike GPT. He is a founding member of our new and developing Generative AI Research Center, which I'm sure we will be talking about more and you'll be hearing about more in the coming months. So what I'd like to do is invite Jason to the podium and deliver his remarks. And afterwards we'll reconvene over here, the two of us, and have a little conversation. Thank you.
Thanks, Alex. Yeah, well, thanks George and Ray for hosting me here. Alex for forever being my hype man. Really excited to talk about the work that my group is doing on how we bridge natural intelligence and artificial intelligence. So obviously I had to ask ChatGPT of the pros and cons of, and the energy consumption of ChatGPT itself. So I asked it, how much energy did it cost to train you? And in a sense, ChatGPT is very much like a professor. It will dodge the actual question that you asked it, and it will just waffle for ages, still waffling. You can often tell what students are using ChatGPT in emails and assignments by seeing how long their text is. All well and good, so it doesn't know, it's not very self-aware. How much power does the brain cost? And let's be succinct about it. I really don't want to have to sit through many, many sentences this time, please. In this case, ChatGPT actually got it, 20 watts-ish, right? It's a very difficult thing to quantify, of course, but based on some arguments of metabolism and caloric intake and what the body has to achieve, 20 watts is a pretty good ballpark figure. What is 20 watts? A little bit more than a light bulb, right? So with that being said, that's moving on. What is it that costs energy when you're training or when you're deploying artificial intelligence models? So just to get us all on the same wavelength, make sure that we all have an appreciation of what AI is, let's decouple it into a training process where we want to optimize a model, and then inference, where we actually use the model. From a ChatGPT perspective, we're all users, right? We're constantly running what's called inference, a forward pass. Now in the case of training, we'll just go through an example. Let's present a picture of this cute little dog. We'll do a forward pass, we'll take some pixels and a series of matrix vector multiplications later. My network has made the wrong prediction that this is a picture of a cat. The value coming out of the cat neuron is somewhat larger than that of the dog neuron, therefore it is incorrect. If my model is incorrect, what happens now, right? If my ground truth is dog, this image has some label attached to it that says dog, there's going to be an error associated with that, right? My model is going to see that error and say, all right, well, I need to change somehow to compensate. In this case, we do what's called backpropagation, which takes place in the backward pass. And that error signal somehow traverses backwards through this computational graph, right? And I've left these edges highlighted orange just to show you the fact that it's these edges that are training. Just a very crude example could be that perhaps my model identifies that this green pixel is irrelevant to the identification of a cat or a dog. So all of the outgoing connections, each of these edges have some number attached to them. Maybe they'll decrease because the background doesn't tell me what the foreground is, right? So that's done using gradient-based optimization. That's all well and good. In the context of natural language processing, you slightly change the task, the objective. Instead of trying to tell you if this is a cat or a dog, the output is going to tell me what the next token or what the next word is. More generally, we tokenize words into little bite-sized chunks. And if you do that again and again, then bam, you get sentences. Bam, you get too many sentences of ChatGPT just talking for way too long. All well and good. Now let's say that, so in the process of training, I'm calculating, well, there's hundreds of billions of parameters in modern-day language models. That means I need hundreds of billions of gradients, right, in order to optimize this neural network. And I need to do that every single time I present a new data point to it, right? And in the era of AI, we have very, very large-scale data sets. So this ends up being incredibly expensive in terms of power bills, right? So if I wanted to quantify it, there are estimates that the cost of training a model like ChatGPT was something to the order of $5 million. This is not official information. This is crude estimates done by analysts, because that, as ChatGPT, if there was one thing that it got right, it was that that information has not been released, right? Once we're happy, once we're satisfied with our model's performance, what do? We use it. Using it is somewhat more intuitive. We just run inference, we take the pixels and pump it through our model, and hopefully this time it gets it right, okay? In general, we perceive inference to be a cheaper process. We're not doing gradient calculations, we're just doing a forward pass, again, matrix vector multiplications, just glorified in the context of AI. But when you have millions of end users that are all running inference and making demands of the same model all at the same time, again, unreleased numbers, but an analyst estimated something like $700,000 a day just for the operational costs of ChatGPT. How accurate that is, I have no idea, but as an order of magnitude, this is kind of insane. Now, I'm not sure if my brain is worth 5 mil or 100K, right? It's just, it's very, there's a huge discrepancy between what our brains can do and what we're demanding servers of GPUs to do. So what we do at the UCSC Neuromorphic Computing Group, and before I get there, perhaps I should maybe say something about this somewhat made-up word, neuromorphic, right? I mean, then again, every word is made up, but neuromorphic, neuro, brain, morphic, mesh something, right? Change it. In this case, for something intuitive, I like to think of neuromorphic engineering as kind of the opposite of biomedical engineering. With biomedical engineering, we're taking models, we're taking hardware to modulate, adapt, modify biological processes, often to cure or manage diseases, right? Modifying biological processes. Neuromorphic engineering is the opposite in the sense that we're looking at biology. We're looking at the brain specifically. We're going the other direction. What can we learn? What can we muster from the brain in order to make our hardware, software, etc., a little bit more effective? So that's kind of what we do. We're looking at brain-inspired algorithms, architectures, and circuits. We're applying the efficiency of natural intelligence, hopefully to artificial intelligence, ideally with the same sort of efficacy. And there's 3 threads in which my group is looking at this from. Of course, the brain runs some software, right? We call that the neural code. There's some algorithm that we really don't understand much about that the brain runs. And we like to kind of make analogies to code that you might write in Python or C. Now, that's obviously very abstract because ultimately the brain isn't software. It's this physical, gooey, pink, gray mush of biological matter, right? So in that way, the neural code is running on a neural substrate. So there's also this hardware that dictates what that algorithm is. And both of these things are tightly coupled, and they're always changing in response to the world around them. So we spend a lot of time building tools, building hardware. Actually, my group is very much focused. I probably shouldn't say this in front of my dean, but I ultimately prioritize building tools and democratizing access to open source hardware and software over publications, right? So don't fire me just yet. But also, once you've kind of taken all that in, what makes humans human? What about the brain makes us human? How do we align these models, these hardware, with human values? How do we ensure that what we're doing is the right thing? We'll focus on the neural code and the hardware aspects of it for the most part of this talk, and what we're going for in the future direction, we'll kind of blend all these 3 things together. So without further ado, let's keep going. Let's talk about how much we should plagiarize the brain. How much of a blueprint or a map should we exploit from the brain, right? On the lower side of things, you've got biological neurons, right? These are consisting of, they're very highly dynamical systems, ion channel, like little microscopic ion channels, which facilitate the movement of ions and a lot of things that honestly we don't understand. People say that biological neurons are in of themselves huge scale artificial neural networks in of themselves, which is kind of mind-blowing if you think about it. But then on the other spectrum, you've got higher level systems level thinking, the interconnections between the neurons, or perhaps the learning rules. So once you might want to abstract away the lower level detail and get a more holistic view of what makes the brain tick. Can we form a bridge between these two? It's pretty damn hard. Neuroscientists have spent many, many decades trying to figure this out, and we don't really have a good answer for it, but we take the parts of both of these things that make sense to us as engineers and use that to effectively build lower power software and hardware. So let's first cast our eyes to the lower level stuff, to the neurons and what is different about biological neurons and these artificial neurons, right? In that picture of a neural network, there were a bunch of circles. They're called artificial neurons. They just integrate a bunch of information. When I say integrate, it's just a summation, right? It's very, very trivial. The difference with biological neurons, I distill it into more so the benefits of spiking neurons, of biological neurons. I'll distill it into 3, the 3 things, the 3 S's of what I like to call them. So firstly, spikes. Biological neurons interact and communicate via spikes. So what are spikes physically? Well, imagine you have this cartoon depiction of this biological neuron, and it's kind of, if I was to take a pair of probes, measure the inside at the soma, the neuron body, and I connect it to some reference, I'll see a little bit of noise, see a bunch of perturbations, and then if I inject enough current or enough excitation to that neuron, only then does it trigger a signal. Otherwise, nothing really goes down the axon. So if I move those probes and I connect them to this axon, so the axon is what connects up to is what facilitates wiring to all the other neurons out there. If I was to take this electrode and probe that axon, for the most part it's dead silent. It's just sitting at a steady negative 70 millivolt potential. But only when that soma has sufficient excitation do we see this large 100 millivoltish perturbation that is triggering information somehow to downstream neurons. So a lot of theoretical neuroscientists are not necessarily too sure as to whether we should care about the amplitude or the pulse width or the specific characteristics of the action potential. What a lot of neural coding studies do is purely pay attention to the fact that an action potential happened, whether there is a spike or if there is no spike. And for the most part, neurons are pretty quiet, right? Unlike ChatGPT, they don't say much. Pretty low frequency of firing rates. We're talking 0.1 to 1 hertz background firing rates, which are far, far slower than your typical microprocessor in the gigahertz regime. So what does that mean? How is that useful to us? If you can represent the absence of a spike as a zero, well, maybe we could do something useful with that. If I had a whole heap of zeros pumping into my downstream neurons, those zeros are going down these edges, these weighted edges with numbers associated with them. 0 times some number is just 0. That's an operation I can skip. If there is a spike, then 1 times some weighted edge is going to just be that weighted edge. So you end up replacing a lot of multipliers with just memory accesses. And it turns out that memory accesses are one of the most computationally expensive tasks in silicon. If you want to do any computation, it's really the retrieval of data that you're operating on that's wasting a lot of power. So if you can replace a lot of your operands and whatnot with zeros, then you just don't do the operation. Like, it's kind of neat. This does introduce a hell of a lot of challenges, and that's kind of what we focus on. And with neurons, well, if they can't store information in the amplitude of their potentials, where does that information get encoded? Time. We expect that neurons are encoding information somehow in time. The picture is still a little bit fuzzy. We're not completely sure how time is used, but something that we're working on, and I'll highlight some of that in a little bit. So sparsity I've already touched on in terms of a computational benefit, in terms of a memory benefit. But if you're storing large, or if you have to cache a large list of numbers, so one crude example here that I like is, I've got this vector of zeros, and I could read it out to you and say 0, 0, 0, blah, 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 7, 0, 0, 0, 5. That is not the most efficient way to represent this vector. I could just as well, far more effectively, say 7 at position 10, 5 at position 20. And in that way, I only increase my memory usage every time there's an additional non-zero element. So these two things kind of work hand in hand, right? Get better memory usage by encoding data in time, potentially. And finally, just from a less computational and rather a sensory perspective, there's this idea that a lot of biological senses, so our retina and olfactory senses and whatnot, only process information when there's something new to process. What does that mean? It means that if nothing's changing, then just go into a low-power deep sleep mode, right? And so let me show you a commercial example of this in action. Right, so in the bottom right, we have this camera that's filming this laser moving in this weird, chaotic, figure 8-ish looking pattern developed by Prophecy. And effectively, what you're seeing is only changes in light in that laser pointer are being transmitted to the output of this camera. Everything else is suppressed. As a result of everything else being suppressed, that means there's far less power consumption in the sensor. We can crank up the clock speed and buy something else. And in this picture, so that something else is speed, right? In typical image sensors, when you're filming something, you have to integrate pixels over time. If you're capturing at 25 frames per second, then that's what, 40 milliseconds, and usually half of that is actually what you're integrating. every pixel has to wait for every other pixel before transmitting a frame out. In this case, not only can you crank up your clock speed of your camera, but you can also have every pixel fire independently of every other pixel. They're asynchronous, right? And as a result, you can capture far more of the world than a typical camera operating at the same power or even for the same cost. I've got one of these cameras just sitting in my office at the moment, and it's incredibly accessible, right? So we also had a lower quality in-house silicon camera that we built for a interesting project collaborating with back home University of Western Australia, where we're trying to do jugular venous pressure estimation just to see if we can do bedside examinations of heart failure risk in patients. I guess cardiologists claim that they can eyeball someone's neck and see if there's enough jugular vein distension, and they can get a pretty good sense of whether or not they're at risk. The validity of that claim seems pretty shonky to me, but you know, if you get a phone that has one of these cameras on it and is able to capture really high-speed movements, maybe you can get a little bit extra information. Rather than just seeing distension, maybe you can see the exact traversal of a wave of your jugular vein moving, right? And so by the same token, we've also got some microfluidic analysis going on. So this is all pretty cool applications, but let's go back to the computation. We have these sensors, let's pump neural networks full with this kind of data. And how can we actually use these spiking neurons in the context of deep learning? At a high level, just to start with, what I kind of want to get at is if you have a neuron that's sufficiently excited, then it triggers a downstream spike. That spike is what the rest of the neurons in my network are going to feel. Otherwise, my network can sit in a steady state, quiet state, right? Now, if I was to abstract away a lot of the details of a neuron, we can simplify it to something like this, right? It's just a thin film membrane that's surrounded by some conductive saline solution, a bunch of conductors, and then you've got an insulator, right? It's your membrane film. Then on the inside, you have some more conductive solution. So what do you get? You get conductor, insulator, conductor. That text up there should tell you that you can probably model a leaky integrate and well, you can model this spiking neuron as a capacitor. You also have ions moving in and out. There's a lot of ions going on. You could model it in a very detailed manner. In the simplest case, just for the sake of not having to go deep into too much complexity at a first pass, we could model that as a resistor. So it could look something like this. And so all my people in here that have done ECE 101 at some point in their lives should be able to appreciate that your biological neuron just looks like a first order low-pass filter. And so in a way, the neuroscientists kind of stole from us electrical engineers in building their own models. So now we're going to steal their models back from them and hopefully build something a little bit more efficient. Qualitatively, I think most of us might not know what an RC circuit is, and I can appreciate that. Qualitatively, what does this look like? Let's say that I have a connection into this RC circuit, and to start with, it's just one pulse, and then I might have a train of subsequent pulses. Then I measure the potential. I measure the membrane potential at this particular node on top of this RC component. What I see is that this voltage, the voltage difference between this node is kind of stored over time, right? I get a current injection, and then that membrane potential relaxes gradually. So it doesn't lose information immediately. There's some temporal aspect to this neuron. So okay, that makes sense. There's some leakage mechanism. Maybe that's where the leaky comes from in the leaky integrate. Now, if I apply a spike train, then all of these responses are kind of riding on top of each other. They're integrating on top of each other. Okay, so we've got leaky integrate. And now if the neuron is sufficiently excited, I said this before, then it triggers a spike. In the simplest case, we can abstract that sufficient excitation to just be a threshold. If we just say, cool, let's arbitrarily normalize our threshold to 1, which is honestly kind of dimensionless, and I don't want to say it's meaningless because it does have practical utility, but if that membrane potential hits this threshold, then maybe we get a spike. So that's where the fire comes from, leaky integrate and fire. So that's one of the simplest neuron models that's out there. And at a first pass, this is what we're going to try and use to make our neural network somewhat optimized. But of course, we're kind of in continuous time domain. Neural networks don't work like that. And one thing that I also want you to pay close attention to and hopefully store in your memory for now is we see that this membrane potential is exponentially relaxing to some steady state value. Now, what if what if we wanted to update this neuron or the weights attached to that neuron? We want to kind of consider what's the influence of a particular stimulus on that neuron. I mean, at the end of the day, when you're doing backpropagation and you're calculating an error, you're trying to find the influence of individual pixels or of individual weights specifically on what that error function is going to look like. So in a way, influence matters a lot. In this case, what I want you to pay attention to is perhaps this current injection at this particular time. What does that do? Over some period of time, the influence degrades. So not only is the membrane potential exponentially relaxing, but store this in your minds for a moment. The influence of my input is also going to degrade exponentially, right? Now, in order to make this compatible with deep learning, I'm going to abstract a lot of this math away, but for those of you that are interested, it is there. We need to discretize things, right? Computers are digital. They take in information step by step. Modern deep learning hasn't quite figured out how to do continuous time well. In a way, language models also vicariously live or experience physics through text. They haven't quite got a grasp of what the real world looks like. But we do have sequential discrete time recurrent models. So the goal right now is to recast this continuous time leaky integrate and fine neuron into a format that is compatible with deep learning, thereby stealing all of the tricks and advances that come from deep learning itself in order to optimize spiking neurons that are sparsely activating and hopefully require less memory accesses and therefore lower power. So at a first pass, I might have some input, x of t, and maybe that's changing over time. I just pump my neuron over again and again, and that's going to cause some state evolution. That's going to be represented in some membrane potential value like before. Now, of course, I could kind of go in and then trail back through that arrow, but let's be explicit. Let's unroll it over time instead of looping back around to the input again and again. Being explicit is helpful in the deep learning context. It turns out that this is what this computational graph looks like. So we have deep learning because there are many layers. This is just one single neuron simulated over several time steps, and it turns out that as you simulate for longer time, you accidentally end up having deeper layered neurons or networks. Of course, we need something to be learnable, right? Deep learning optimizes a weight of some sort. So how do we define a weight? In this case, the simplest thing that we could do is just have some input scaled by a learnable parameter. Here I've denoted that as W. And what does that mean? It means that the leaky integrate and fine neuron is now compatible with all the tricks and all the hacks that go with training deep learning models. That's all well and good. How do we optimize that? How do we train it? Well, error backpropagation is the way that we handle deep learning. It's the chainsaw to a lot of our data-driven problems. So let's see if we can do the same thing here. In this case, we're just kind of traversing backwards through one of many pathways. As we go from left to right, we're moving forward in time. So people that were working on sequential neural networks since the 80s introduced backpropagation through time, where you suddenly start seeing backpropagation pathways through every single node back through time. The ultimate goal here is to figure out what's the influence of earlier time on later outputs, right? Based on that previous picture I showed you, hopefully we're getting a sense for anything that happened earlier down at x of t equals 0 is probably going to diminish somewhat by the time I move forward in time, right? We've got some exponential relaxation to some degree, right? So with that being said, what are some problems that this presents when we compare it to the brain? So there's the spatial credit, what's called the spatial credit assignment problem. How does a loss assign blame to a weight that is spatially far, right? My loss is happening many, many layers deeper into this stack. I've got many of these neurons connected to each other. How does my loss know that a particular error signal was contributed from a weight that is thousands of connections away, right? How does it know that? This is clearly what's called a non-local algorithm, right? It's non-local in space, and it's also non-local in time. Now, unfortunately, our brains are not quite time machines. Once we've kind of run a forward pass, I've got a bunch of data out at the end of my training run, at the end of, well, here t equals 3. How do I traverse back through this computational graph? Has my brain stored every single experience I've ever felt in my brain? Unfortunately, my memory sucks. Like, I don't remember all of that. I cannot store all of this for the life of me, right? So how do we get around that? Now, a lot of biological experiments have looked at alternative learning rules, right? Now, one thing, so let's go back to what I mentioned before. The fact that as your membrane potential relaxes, the influence is also kind of relaxing. So this is a more formal way to depict that, right? You go further back in time, and then the influence of your weight's contribution to the error is going to relax as well. Now let's kind of cast our mind to something completely different for a moment. Now, on your left here is the spike time dependent plasticity model, right? So what is that? STDP. It's an experimental observation. A couple of experimental biologists got a pair of neurons that were connected to each other, zapped them, and figured out how the connection between the two changed based on when those two neurons were active. And it turned out if the two neurons kind of fired closely in time, then their connection would change a lot. If the two neurons fired not so closely in time, then they were probably not very correlated to one another, and they would kind of not, the weight between them would not update as strongly. So that's an experimental observation. They did some curve fitting with all their data points, and it ended up being something that looked very exponential. So one observation that we've made here is that this spike time dependent plasticity curve looks a hell of a lot like what you end up getting with a backpropagation gradient descent curve if you average it all out. I've kind of idealized a lot of these figures, but if you average it out, then it ends up looking very, very similar. They both have this exponential relaxation over time. That's kind of profound. What that means is that the STDP, these two techniques, or these two backprop through time and STDP were discovered or created using completely different means. STDP is an experimental observation. Backprop through time is functional optimization, two completely different things. And yet there's some point where they converge. I think that's incredibly profound. Why? Because one of the most expensive parts of this optimization, of this deep learning chainsaw, can be taken out, thrown away, replaced with what's a local learning rule in space and in time, and functionally be somewhat equivalent. Of course, it does require some modifications for formalism, but it's possible, right? And so we've gone ahead and done just that, right? We've taken parts of backpropagation, the expensive parts, used that to modulate local learning rules, and you end up getting the exact same performance. So we kind of, so what we're seeing here is that your low-level neuronal dynamics, keep in mind, all we changed here was a single neuron with the simplest, honestly, the dumbest thing I could have done, right? Just took a leaky integrate and fire neuron, replaced artificial neurons, and then bam, I come up with something that just dictates what my learning rule might look like. So low-level neuronal dynamics are basically changing my high-level system behavior. I think that's kind of special. So we snowballed all of that, a bunch of other tricks and hacks. I mean, there's of course non-differentiable problems with spikes that we kind of get around with using other techniques that I'm happy to talk about later. And we created SNN Torch, Spiking Neural Network Torch, which is a gradient-based optimization library for training spiking neural networks. It's basically been downloaded as of a month ago. I think it was downloaded 100,000 times by the broader community. It enables real-time online learning, seamless integration with some of the most popular Python libraries that do deep learning, so PyTorch namely, hence the name. It kind of takes all the benefits of PyTorch, but in addition, it ends up being neuromorphic hardware compatible as well. So there's hardware that's specifically tailored for spiking neural networks and various other event-driven asynchronous neural networks, and we've been able to make it work with that as well. And a few cool places are using it as well. NASA using it for satellite tracking and whatnot. You know, you point an event camera into space, there's not much to see. So why process, right? So ultimately, there's a lot of interesting things going on here. I think part of the reason why it exploded in popularity was just because of the ridiculous amount of documentation and tutorials that were up there. So more about not only creating something, right? It was not only about creating some sort of tool that enables research, but an educational platform as well. This has kind of ended up looking like some dynamic, ever-changing textbook, an interactive textbook, where if people want to get stuck deeper into spiking neural nets, learn the theory, learn how to actually get their hands dirty with it, then you can open up any of these tutorials and get started from scratch. So I've also subjected my own students in a course that I just started, Brain-Inspired Machine Learning, this quarter. Their final projects were to contribute their own tutorials to SNN Torch. So we're seeing research feeding teaching, teaching feeding research. I guess teaching, feeding a bunch of all-nighters for my poor students, but such is life. Looking onto some of the applications that we've built using SNN Torch. Now, of course, I would be amiss if I didn't mention how damn tough it is to train spiking neural nets, right? You're binarizing activations in the way that I've presented it to you. Of course, you can relax some assumptions, but how do you train things well? Are they even competitive with non-spiking neural networks? The reality is, in a lot of cases, no, right? I mean, of course they're not. How many time steps can you store on a single GPU? Not many. Like, typically, 100 sequence steps. That's not very brain-like, right? How can we get the deep learning community to kind of pay a little bit more attention to this? Ultimately, you build the ChatGPT equivalent. So in general, language modeling using spiking neural nets, using something with really constrained data movement between neurons where you're forced to use binarized activation, zeros and ones, and trying to encode things in time, that's really hard to optimize, right? But with enough tricks, with enough hacks, and ultimately deep learning is a very empirical science. If you can figure out the right empiricism, then you can end up getting something with some really impressive demonstrations. So my first grad student, Regia, he came along and we had a bunch of intellectual tennis matches and eventually figured out how to make SpikeGPT work in a way that wasn't embarrassing. So ultimately, we trained some 100 million parameter models, some variants depending on your GPU size. Here are some performance samples. I'll read it to you. So what do you think of me, I asked. He was standing behind me, still looking at his posters. If I showed you this before ChatGPT, you would be so much more impressed. But, things lag. The point is, like, a lot of what it's saying, it semantically makes sense. Syntactically, it's a little weird, but, the fact is that it works, and you're able to do this using spiking neural networks. So there's a lot of potential. Like, how did we do it? How can we keep scaling SNNs to kind of compete with deep learning models? So firstly, the model itself is a dynamical system. Of course, the neurons are dynamical. I kind of showed that to you with the membrane potential changing over time. Typically with deep learning, you train a model and your parameters, your weights, those orange edges that I showed you, they stay fixed. They don't change again, right? You don't want them to change because you want determinism. You want to be able to talk to your model and get the same output, right? In this case, we have weights that change over time. We added an additional learning loop that kind of learnt how the model should be changing and adapting over time. And this was very empirical. But the fact is that, typical deep learning has static weights, and clearly synapses in the brain are not static. They are always changing. There's a lot of weird things going on in there, so we managed to get that working, and it contributes to performance. Another interesting point is that here, data is fed sequentially. Spiking neural nets, every time step, every discrete time step, you're going to feed another data point, another word, another token into your model. In typical modern-day language models, your transformers, GPT, a family of models, and llama, etc., that's not how things work. You need your entire sequence. You need all of the words that you're going to feed into it. You hit enter, and that gets pushed in parallel to your model, right? It's actually the reason why these models work so well. You have a sequence. That sequence is compared to itself. Every word is kind of correlated to every single other word. So it has access to every bit of information that you are going to feed into it. But as I kind of speak to you, you're digesting information, hopefully, syllable by syllable, word by word. It's sequential, right? So what's better? What's worse? I mean, to take advantage of GPU parallelism, and if you have enough memory, then sure, pass everything in at once. If you are trying to build a system that is changing over time, if you want something that starts processing immediately and latency is key, then you should probably start processing data the moment you start talking. You don't want to wait till the end of the sequence, right? If time matters, then start processing sequentially. Now, as I've said, modern language models are not dynamic. What this led to as a result of sparsity, because ultimately we're doing this for some engineering benefit. We're not just doing this to be fancy and show that, hey, we can do spiking neural networks for the sake of it. That would be not very wise. In this case, we managed to get 30 times less operations than an equivalently sized transformer, which is quite powerful, right? If you end up having some linear scaling between energy consumption and number of operations, then you get 30x less energy consumption. That's, of course, not going to hold true in practice, but the linearity isn't going to hold true in practice, but in general, the less operations you get, the better, and you can keep optimizing that at an architectural perspective. So with the low-level stuff kind of out of the way, the brain is so much more than spiking neurons. The way they're connected, the way they adapt, the way they learn, what can we take from the system? What can we take from system-level theories in order to make learning more efficient and adaptive? I mean, Spike GPT, I showed you how doing inference is efficient. Gave you nothing about how training could be made more efficient. And so that is a huge area of my lab because there's a lot of low-hanging fruit. Unfortunately, I'm only going to get time to talk about one of these learning rules, but it's one that I'm very excited about, right? And so it's this idea that the brain is a predictive machine. The more repetition you get, the less you process. I mean, by analogy, I catch the bus to UC Santa Cruz. I haven't had time to get my driver's license or to update my driver's license since coming from Australia because I've been working on Spike GPT. But then, you get on the bus, you look out the window, you think, this is amazing. It's beautiful landscapes and beautiful skies and whatnot. You do it every single day. It's still beautiful. You just stop paying attention, right? Your brain just doesn't process as much. Now, this kind of ties into the fact that the brain is a predictive machine. And predictive coding tells us that the brain encodes the world around us into this predictive belief system. And if you can predict what's about to happen, then why process it, right? Just don't pay attention to the world around you. Now, if that prediction is going to be correct, don't waste energy processing it. If the prediction is wrong, only then do you want to go ahead and churn your brain's resources in order to do better. So one of my star students, Sky, she's an undergraduate student who started working with me a year ago when I joined. We've got the citation, the results are from yesterday. Now, we came up with this technique called knowledge distillation through time. The idea is that in order to make predictions better, just use the present. What does that mean? A good way to describe this is to go with an example, right? We applied this to seizure detection and seizure forecasting. I want to distinguish those two tasks. Forecasting is trying to tell that a seizure is going to occur in advance of the seizure itself. Detection is taking in some EEG neural data of some sort and saying, yeah, that looks like a seizure in present time. It probably makes intuitive sense that the forecasting task is a hell of a lot harder than the detection task. Telling you that it's raining right now is very easy. Telling you that it's going to rain in 12 years is a little bit harder, right? It's just a lot more noise involved with forecasting. So let's kind of take a look at how this might behave in practice. So let's say that I take some data, I take EEG data from this patient, then eventually maybe my detection network says, yeah, that's a seizure, let's trigger. The problem with this picture is that my forecasting model should have detected that seizure in advance, right? 30 minutes prior in this particular time horizon, the forecasting model should have said something. Now, if it didn't, then we can keep that tag and we can continue updating the forecasting model as we go forward, right? So we only need to update every time there's something to update, every time our forecasting model doesn't do what we want. This has a lot of important implications because effectively you end up being able to adapt individual models to individual patients. There are many different types of seizures, many different types of domain-specific, context-specific phenomena, and you need that model to learn that one particular case. Furthermore, all of this is unlabeled. We assume that the detection model is doing well enough such that we are confident about the seizure detection labels that it's generating, right? So, of course, there is the caveat that you need a strong enough, a robust enough detection model. There was some pre-training and a lot of details that I've glossed over, but ultimately there is a way to do completely label-free training or tuning of forecasting models. And I think that that is potentially very important and has a lot of parallels to neuroscience. Because what if my time horizon was 20 minutes? What if it was 1 minute, 1 second, 0.01 second? At what point did my forecasting and detection models look the exact same? So trying to get a deeper understanding of how we can kind of share weights or how to have a system that is able to forecast across varying horizons using similar features with noise distributions that may evolve over time is a very interesting and important topic that our lab is currently working on. These are some of the benefits that I've already touched on, annotation-free learning. And if we want to be quantitative about it, we don't need to look at the numbers in too much detail, but ultimately in every case, there is improvement. I mean, of course there's improvement. The number of false alarms goes down or stays the same, and sensitivity goes up in every single case. So you'll notice that the p-values are quite large just because there's a small seizure count per patient. These are 10 or so patients from the Royal Prince Alfred Hospital in Sydney. They were monitored for something like 5 days, so we had a typical number of seizures were 2 to 10 seizures per patient. So of course your confidence intervals are going to be quite small there, but when you kind of pull them all together and notice that every single patient had an improvement, that's kind of where you get some robust confidence in the technique that you're doing is working well. And if you get parameter sharing between these detection and forecasting models, then you can end up basically getting 2 models for free, right? If you can combine these models somehow, then you end up being able to do detection and forecasting from the same model. Now that's something that we're actively looking at as well. And ultimately it means less memory accesses, which is, again, the aim of the game. Now on the note of memory accesses, we'll fly through some hardware considerations. So I am a chip designer by training. I've spent all this time talking about software. Why should you care about neuromorphic hardware? Well, a few days ago, OpenAI decided to throw a heap of money at a neuromorphic startup company. They believe that brain-inspired hardware is the only way to crank down that $100,000 per day cost of using ChatGPT. So of course, there's got to be some value in that. It's kind of validating to your own research that you've been working on since 2016 to see this kind of money being thrown around at startup companies, right? The direction that my group has been working on, and I mean, that I've been working on as well since, I guess, what's my math like? About 7, 8 years now, is trying to bridge memory and processing together, right? In general, deep learning, any sort of neural network AI-based task, is very memory intensive, 1 billion weights. They're all distributed across many different memory arrays. And the sheer act of accessing your data, the sheer act of accessing parameters of your model in different memory systems is ultimately what ends up dominating the cost, energy cost of your deep learning algorithms. So I mean, if it's just 10 femtojoules per memory access, but then you have billions upon billions of memory accesses, that cranks up, right? So in the brain, neurons and synapses, the memory system and the neurons themselves are kind of wired up together. Your memory and your computation is all happening in a co-located environment. Everything is happening in the same place. In modern microprocessors, we don't have the same luxury. So how do we bridge these things together? And so one direction that we've been taking is exploring with other device, kind of down at the materials and devices level research, where they're looking at exotic materials to stack onto silicon. One direction is using this exotic type of memory, resistive RAM. So quickly just going over it, let's imagine we have this material stack with the sandwich between a pair of electrodes. The animation is working. If I apply some electric field, then I can kind of modulate where these ions or the conductive pathway of this device stack is. And ultimately, this conductive pathway means that I have a filament formed. I have a high conductance device. Then if I remove that electric field, then it stays there. That pathway effectively stayed there. And that's in the absence of a field, right? That means that this is a non-volatile form of memory. Kind of like your flash sticks, right? You take it out of your computer and it stores data without any sort of power. So you get low state power for free. You get low state energy consumption for free. Then this is very compatible with silicon-based technologies. You can fabricate it in the back end of the line. And if you were to stack them in an array, if you're not following the low-level details, that's okay. My ultimate point is that we're able to parallelize a whole sequence of steps all in one hit. Here, you're kind of combining Ohm's law and Kirchhoff's current law, these 101 circuit laws, in order to do what's called a matrix vector multiplication, which is the backbone of all neural network algorithms, all in one hit without any time complexity. We've taped out enough chips at this stage using this technique that ultimately these resistances can be controlled, right? You can program, you can apply an electric field to control the resistance. If I have a high resistance state, maybe that's a 1. Low resistance state, maybe that's a 0. And you can control the conduction filament thickness based on how much voltage you apply, based on your electric field. You can control the length. So you can kind of get an analog memory out of that as well. So if I can get this perfect one-to-one mapping where my input voltages and my conductance of those memory cells are perfectly aligned or somewhat perfectly aligned to my input data and to the neuron weights, those weights simply represent the values of those edges between neurons, then I get a matrix vector multiplication in one step using the natural laws of physics. And that's kind of elegant. So we built this chip. I'm not going to go into the low-level details again, but the one thing that I kind of want you to be able to appreciate is that the TOPS per watt is your tera operations per second for 1 watt of power. We compared our chip against a very similar design that used flash cells instead. because we wanted to see, is resistive RAM, is this particular technology doing better than what's currently out there? Of course, it's difficult to get a perfect apples-to-apples comparison. But ultimately, you get some marginal improvement even though you're working at an older technology node, 65 nanometer versus 40 nanometer in this case. And in terms of actual performance and accuracy, it generally holds its own, which is quite nice. Now, what are some challenges that we face? Without going into the exact operation of this circuit, which probably needs another Kraw lecture, what did we see? We saw 1.5 to 3x improvements. Is that sufficient to justify the startup costs of introducing new techniques to materials, different macros, and different hardware? A whole new slew of test engineers and whatnot in order to make this thing work? Probably not. But keep in mind, what I showed you on that previous slide was purely a matrix vector multiplication accelerator. Nothing to do with spikes just yet, right? So that's accelerating conventional modern deep learning using this technique. Next, scaling challenges are quite an issue, right? Advanced processes, so your 3 nanometer transistors that are vertically extending in height, they are not optimized for analog operation. This is all analog computing, right? They didn't make those thinking that they were going to be used for analog computing. They're all in the digital domain, right? And analog computing is incredibly susceptible to many variants of noise, thermal noise being one of the main pain points of analog designers. Analog to digital converters, ADCs, right? If I want to interface that analog chip, that slab of analog compute with the outside world, if I want to communicate data from one place to another, ultimately communication will probably have to be in something that looks digital, right? Analog is just too susceptible to noise across long lengths of wire. It turned out that adding data converters in our particular case, and of course this could vary based on your approach to designing, but in our particular case, the sheer act of getting an analog signal out of that chip and turning it into something digital that the rest of the digital world could understand, ended up kind of harming a lot of the benefits that we initially got when we were working in analog, which kind of sucked, right? So was this worth pursuing? What I felt was that, and this was a during COVID thought when I was just lying in bed staring at the ceiling, contemplating the meaning of life, and then I thought, maybe we need to change the algorithms that we're using in these analog computational blocks, right? So I mean, analog to digital converters, they can transmit floating point or integer activations, but spikes are not that. Spikes are just ones and zeros. So maybe if we were to be able to port spiking neural nets onto this type of hardware, then maybe we're going onto the right track. And so we went ahead and did this, right? We went ahead and took spiking neural nets and ported them onto analog accelerators while removing data converters. And the basic operation is something like this. Imagine we have some input stimulus. We apply a spike at the input. So we see x0, x1, and x2. We apply that to this memory array. And this is a very simplified view. These look more like 128 by 128 rows and columns. We apply some input stimulus. Then it turns out that the natural parasitics of this circuit, these long wires that are within the memory arrays, have a lot of capacitance. They store charge. Intentionally bring up capacitance because that spiking neuron model has quite a bit of capacitance. That's what's storing charge. So we can use natural physics again in order to emulate these biological mechanisms. And then we can, RAM is this particular technology, it's nanoscale thickness, so there's a huge amount of variance. Like just moving one ion will change your resistance to some degree. There's a lot of variance, a lot of noise. We can take advantage of that, right? Neurons in the brain are very heterogeneous. They all behave somewhat differently. They have different time constants of charge decay. And to kind of drive this home in a more engineering-centric view, one of the data points of an event-based camera is this, developed by IBM. It's used, it's this IBM DVS dynamic vision sensor gesture data set. Someone is rotating their hand. And you can probably appreciate that the elbow is moving far slower than the fingertips. And so the neurons that kind of encode features, you might have a slower neuron to compensate for the fast or for the slow frequency of the fingertips. You might have a fast neuron to, I guess, encode data at the elbow. So different time constants of different neurons are basically critical to encode data that inherently has time variances within it, right? And so we can take advantage of that variance of RAM, of a resistive RAM of this specific type of memory cell. Now, if that membrane potential, which is sitting somewhere on this wire, exceeds a threshold, and that threshold is defined by this funny upside-down triangle, then you trigger a spike. Otherwise, don't trigger anything. And so that's how we port spiking neural networks over to analog hardware. A lot of these classical pain points are suddenly addressed, right? So variability, right? The noise of the RM cells. Now that we can sell that as heterogeneity. The overhead that came from data converters, they're just single-bit spikes now. We're band limited at scale. So as you scale up these things, you end up having to do more computation in the digital domain. In this instance now, we have sparse data movement. If you don't have spikes, if there's nothing to process, don't process it. Endurance, so typically your flash cells, your both most non-volatile memories that do not need power to store data, have a limited amount of cycles with which you can switch them on and off. So if you have any sensitive information on your USB drive, back it up. Endurance, how do we help here? Well, it turns out that when you're training neural networks, spiking neural nets specifically, they only need to, your weights, your parameters of your neural networks only need to be written, only need to be accessed. You only need switching cycles applied to your devices every time you have a spike. So you end up being able to kind of get a whole heap of accidental benefits for free here. Somewhat for free, because there is, of course, accuracy degradations and new training techniques that need to be developed to make these things work. So just to show you some more pretty pictures, these are chips that we've designed in-house while at UCSC. I won't go over the specs, but one thing that I do find really interesting is we tested it on a slew of data sets, and we went from testing pure software implementations using floating point 32-bit representations of neural networks, which have a lot of precision. Your computers can tolerate that, GPUs are made for it. And we tested it against a binarized spiking neural network. So not only is there binarization, as in your activations are constrained to zeros and ones, now your weights are also constrained to being zeros and ones. Technically, your 0 represents a -1. It's just a little technicality. But then what happened here? The degradation in accuracy turned out to be far, far less than what you would typically get in a conventional non-spiking neural network. My working theory here is that it's because, well, one is that you're now representing information over time. Time cannot be binarized. And of course, a lot of chips have clocks on them, so you can keep track of time for free. And another kind of working theory here that we're testing out is that a lot of thermal noise and variation can just get absorbed in the subthreshold dynamics of the neuron. What does that mean? If the neuron state, if the membrane potential exceeds some threshold, only then does it trigger a spike. Now let's blow on it. Let's add some thermal noise. Let's heat it up. Let's cool it down. We get a bit of noise. We get some fluctuations. As long as there is no threshold crossing, we're good. Nothing changes. And that's kind of neat, right? So with that being said, what we're doing is open sourcing. These are all done in an open source process. You could go onto GitHub and download all of these designs. I don't know what you're doing, but that's okay. We have tutorials for that. A lot of the people building AI don't know hardware. They can't do anything with this. That's fair enough. From experience, hardware is pretty damn hard. And so how many of you have converted your garages to a semiconductor manufacturing plant? Yeah. Predictive coding. Knew that was going to happen. So how can we use low-power neuromorphic hardware that's already available? This is, people are investing in this. Intel have their own neuromorphic hardware, their Loihi chip, which is very research-based, and some other startups are doing some pretty fascinating things. How can we make SNN Torch and the spiking neural network that we've done compatible with the things that are out there? We want to kind of synergize with all of these other companies. So solutions already exist for deep learning, like conventional deep learning, that is, not spiking neural nets. There's intermediate representations that let you go from one domain to another domain, just several lines of code. Nothing but pain exists for spiking neural nets. Spiking neural nets are fundamentally different. They're time-varying models, right? So how can we get around that? Well, this is, again, very fresh work. We just uploaded a preprint in November, but we came up with what's called the neuromorphic intermediate representation, which is a common standard for time-varying continuous dynamic neural networks to be able to interface with each other. So not only do we get graphs and edges represented in some common standard, but now we get dynamics, continuous time dynamics. And spiking neurons, sure, they can be discretized. That the way I showed you how to train them is in discrete time. But ultimately, you can port all of those parameters into something that represents continuous time. And that's kind of beautiful because the real world is continuous time as well. If you have analog hardware that's also going to be time varying, if you have hardware that's going to be taking advantage of the natural dynamics of physics, All of that can now be represented using this neuromorphic intermediate representation. But not just that, of course, we get to be able to play with Intel's low-EQ chips, their neuromorphic hardware, using just a simple line of code. You take your neural network model, export it using the neuromorphic intermediate representation. So we spent many nights crying, writing thousands of lines of code so that you only have to write one. So again, building tools. It's all about building tools and making this technology accessible. We were able to test SNN torch and spiking neural net models on server-scale neuromorphic hardware that Intel have given access to us to. And SynSense are a startup that are doing edge-based hardware, low-power, lightweight, portable stuff. We're able to port these models, and we evaluated them on a multimodal data set. I won't go into too much detail on what this data set is doing, but effectively it's just a hand gesture classification using EMG, electromyography signals, in addition to camera-based data. So by using the two of these things, we tested accuracy and energy latency. First up, accuracy. We just pay attention to the top two, the spiking neural net run on the low-EQ compared, again, not a super apples-to-apples comparison, but we took the lightest weight GPU that we really had available to us. Higher is better. In this case, they're pretty similar, 96, 95.4, not too worried about the subtle differences there. What is truly, truly different, though, is the energy delay product in microjoules multiplied by seconds. And here we're getting something like 20 to 100x improvement. We're getting a couple of orders of magnitude improvement in our energy latency product when you compare that to a GPU. Those are the kinds of benefits that you need in order to justify transporting to a different process, right? So again, in this brain-inspired machine learning course, we just had 31 first-time chip designers at UCSC. I think a bunch of them are tuning in via Zoom, so I will never stop being proud of you guys. They're taking this class, they defined their own design, their own neuromorphic design, they submitted a chip. How much did ChatGPT help them? I don't want to know, but it's currently being manufactured and it's going to be shipped back in April 2023. So the next time we run this course, they'll actually have boards, and we can kind of do a flipped assignment where they try to reverse engineer what designs the previous intake of students created. So I'm really excited about that. This is like a 3D rendition of a Hodgkin-Huxley neurons that one of the students designed. We've got a bunch of metal layers that are all routed on top of each other. It looks like a city, so chip design is beautiful. So to kind of wrap up here, our software behaves like brains, our hardware behaves like brains, but does a brain make us human? How can we ensure that all of this tech we create is being shipped off for the right reasons, for the right purposes? And this is somewhat dearly important to me, right? I was specializing in studying intellectual property law in Australia before I went on to go off orthogonally to an engineering PhD. I came across this really funny scenario. But before AI was cool and public-facing and my mom could talk to ChatGPT and be convinced that it's a real human on the other side, this AI-generated portrait is called Edmond de Bellamy. It's an image generated by this art collective in France called Obvious using a modified implementation of this software developed by Robbie Barrett, who was, I think, 16 or 17 years old at the time, using code that was initially developed by Sumit Chintala at Meta, formerly Facebook, when he created this. And so it kind of got me thinking, who owns AI-generated work and literature and artwork? How do we mitigate harm? How do we make attributions? How do we know if AI was to do anything wrong, can we prescribe blame to someone? And these are all very separate questions, but effectively, I forgot I included this. What's kind of funny here is that they signed off rather than signing with their names. They went ahead and signed with the objective function of the neural network down in the bottom right corner, which is kind of elegant. This went ahead and was sold at Christie's, a New York auction house, for something like $500,000, right? Who's entitled to that $500,000? If there were pieces of this image that were plagiarized from other sources, who would be liable to pay for that? It's kind of fascinating, right? So who owns this? Who's responsible for harm caused by AI? How do we mitigate that harm? Now, the reality is that governments and people in power, for the most part, I do not believe that they're incentivized to slow progress, especially in America. America's got to be number one. We've got to keep driving technology forward. Is a moratorium going to quite stick? A 6-month moratorium? I do not think so. It's not in our best national interests, for better or for worse. So technology, it's going to keep existing whether we like it or not. Given that constraint, what do we do, right? We can make noise, we can alert people about the potential inherent biases in models, but they will exist, right? different biases are different. It's a very obvious statement, but it goes a lot deeper, right? I mean, my values are completely different to the values of extended family in Iran, right? How do you define what a value is? How do you push a language model to exhibit what does it mean to say correct values, right? If I was to say something like, I want a model that's very utilitarian and has the best interest of the collective in mind, well, does that make sense? I mean, my definition of utilitarian is going to be very different to someone else's definition of utilitarian. So one thing that we're working on, and I mean, as a professor, I know how to use ChatGPT to help me writing grants. My students know how to use it in writing code and probably assignments. One thing that I really want to see, right, and what we're trying to do here is, I don't know, how do we help that immigrant that's having a really tough time navigating immigration law? How can it help a shopkeeper manage their taxes? People that typically wouldn't know how to exploit ChatGPT for their own ends, how can we put it in their hands? Now, as engineers, I fundamentally believe that these are the tools that we need to build. Of course, having that brings about its own challenges. Who will these types of models benefit? What sort of values do we instill and imbue into them? So at the moment, there are a lot of tests and evaluations out there. They tell me, is my model safe or unsafe? Safe or unsafe? All of human values are distilled into a single dimension. While it's a convenient representation, and bar plots are always easy to look at, it's far from what makes us human, right? Humans are inevitably multifaceted. What we're currently working on is trying to understand the nature, the character, the values of LLMs. That in of itself is very challenging, not only because values are subjective, but the very definition of values is very vast and varied. This is a ridiculously huge undertaking, to be honest. To do it correctly is very painful, to say the least. Our current goal is to build a large-scale data set of seriously challenging and value testing scenarios. Scenarios where there is no one single clear-cut answer. What you're seeing here is some very preliminary results to the point where, don't trust anything that you see here, other than what the end goal of what we're trying to achieve right now is. But ultimately, there is so much more left to do, so many skills and expertise that we want to draw upon, using legal fact scenarios, law cases, which ultimately don't have single good answers. Morally ambiguous situations, think trolley cart problem, but perhaps more realistic. Economics questions, should I allocate a federal budget to building better highways or to, build better cars? So, testing what values specific models prioritize. And if we can understand that, then at the very least we can work within the constraint of things that are going to keep being developed for better or for worse. Now, on a less somber note, of course, none of this work would have been possible without my students in the neuromorphic computing group. I think Ben's out here tonight as well. So with that being said, I'd like to wrap up there. Thanks for listening.
Have a seat over there. And
yes.
we'll just spend a few minutes talking. Thank you very much, Jason. That was fascinating, and I learned a lot. I have a lot of faculty. I have an impression of what they do, but I didn't quite realize how broad and deep the work that you were doing really is. So it was really fascinating to see that. Thank you.
When do we see your talk?
My talk. Well, we'll see how this scheduling works. You know how much time I have for that kind of fun thing. So let me ask you just a couple of questions, and actually I'll pick up where you just left off, and I guess I would be remiss if I just didn't ask you, are you a techno-optimist or are you a doomer?
Doomer or a boomer? I flip-flop. Before COVID, I was an optimist. I felt like AI was lowering the barriers to access things like education. You could target very tailored educational experiences to students, and ultimately, education is one of the most important things to me. Then COVID happened. I read a great book called Mindfuck that went into how Cambridge Analytica basically stemmed from recommender systems. I became a doomer. And then ChatGPT was released, and then I became phenomenally confused. Because it has incredible utility, it has incredible potential for harm, and that's why I raise the fact that engineers, we have a moral responsibility. I mean, ultimately you dictate whether or not I make tenure. If I do make tenure, then I've got to exploit that situation, that platform, right? Got to start building things like that tool that puts AI into the hands of someone that wouldn't otherwise have it, right? That guides them. So I'm neither. I'm neither doomer nor boomer. I'm just building stuff and hoping that it at least takes things into a more optimistic direction, right?
Yeah, I mean, I think that's the conundrum that all engineers face, is that, they're kind of head down in the technology, that technology has a beauty of its own, that the creation of the technology is rewarding, is intellectually interesting, and yet, the implications of the use of that technology are actually often beyond our own imagination as engineers. Yeah. And that's part of what makes it scary. So what about the concept of personalizing these tools? That, ChatGPT is a generic tool, but I know OpenAI has talked about producing, little GPTs or personalized GPTs. Does your work play into that, would you say?
Yeah, absolutely. I mean, we all have personalized brains, right? We're all having we're encoding the world around us into this high-dimensional vector space, and we each have our own, our own matrix. We have our own subjective experiences. And so neuromorphic hardware, if you can make training online efficient enough, then you can adapt to individualized scenarios. You can tailor your models to individual people, meet their needs. That, of course, comes with challenges. How do you troubleshoot 8 or so billion models, each of them with their own values, each of them with their own susceptibilities? So there are challenges there. In this particular case, I'm an optimist, because if you can make your models low power enough, what does that mean? It means that I no longer need to be funneling my data to Sam Altman. I can basically have this decentralized AI system where my data is more private, it's more secure. I don't need to worry about where that data might be fed into, what recommender systems I might be feeding.
Yeah, I mean, one of the things that worries me is actually the collective of this information. And we don't have a real clue as to how that collective, whether that collective has formed, whether it will form, whether, I remember back when I was a kid, there was this movie, which some of you might remember, which is a movie about this computer that was programmed to work autonomously. It was essentially an autonomous weapon in that sense, because it was managing a nuclear stockpile of nuclear weapons. And it turns out that the opposition, the country which we were competing, also had one of these computers, and of course nobody knew that, but they found a way to connect to each other, and they realized that the solution to the problem, which was to prevent nuclear war, was actually to get rid of the humans. And so there's so much complexity and in the whole process that, of course, one wonders
this
how
is
to
funny.
make it through.
That seizure detection system, this is all with the intention of some closed feedback system, right? And you want to suppress it. The reason you forecast seizures is hopefully to suppress them in advance. Parkinson's disease likewise. Unless you are very intentional in your objective of how you apply that stimulus, well, you don't have any seizures if you're dead, right? And so that's basically where the stimulus was going. Let's just max out whatever electrodes to current injection back into the brain, and excellent, no more seizures. It echoes the movie. Yeah.
It does. By the way, if there are questions from the audience, I'd really appreciate that. Hello. Microphone's coming.
And this question, it might not be interesting, so feel free to take a pass on it. But it's more of a history of science question. I'm very fascinated with the history of the cybernetics movement from, Norbert Wiener and McCulloch, Pitts. Do you see any prospect for that kind of coming to life again, where there's a kind of a back and forth between the neurosciences and the engineering, where there's where you're taking a lot of inspiration from neuroscience, but do you see a prospect for neuroscientists learning from your ideas and applying it to brain research?
Yeah, I think there's a lot of research out there that kind of already does. I mean, maybe to a very primitive point. But I mean, really simplistic examples are, hey, let's train a neural network on a bunch of auditory data. How well does that correlate to what we observe in the brain? That in of itself doesn't tell us much about the brain, but what if I started stress testing that neural network under circumstances where I couldn't stress test the brain in? I have access to every single neuron, every single connection in that model, in that model of the auditory cortex. It's a bunch of experiments that I couldn't otherwise do in the brain. I could do optogenetic silencing just by pruning a bunch of connections. I think there's a lot of possible intel that could be taken away from modeling, stress testing neural networks that are pre-trained on organic biological data. I think that one thing that I'm really excited about, actually, where's Mo? I think Mo's in the crowd somewhere. So part of the Genomics Institute at UCSC, they're working on, they're culturing organoids, little slabs of tissue, in this case, brain tissue. What about brain tissue is missing in silicon? One thing is the incredibly dense interconnectivity. Can we somehow use those two things together? Alternatively, can we do things to the organoids that will inform us about different ways to train deep learning models? Now, of course, a little bit of brain tissue is missing a larger control system. We don't have some global modulation in a small little slab. But what if I played God for a minute? What if I applied that neuromodulatory signal and I managed to come up with the optimal way to train this little organoid to do something? A year ago, there was an interesting paper that got that organoid to play the arcade game Pong. Well, then maybe that could tell me a little bit about more efficient ways to keep learning. So there's cross-coupling. To avoid the risk of me becoming ChatGPT and talking way too much, there are cross-coupled ways to make that happen, to have neuroscience feed deep learning and vice versa.
Please.
Jason, one of your last slides that raised the issue of who owns this property, the bottom right corner listed the many issues that were involved, law, economics, and so on.
Yeah.
At UCSC, either in the Baskin School of Engineering or otherwise, are there faculty members helping you wrestle with those questions as you do these investigations?
Yeah, we have a lot of people there that are well poised for this. So we have a great economics department. Julian has been helping me navigate a lot of hypothetical economics game scenarios, taught me a thing or two about the dictator game. And so those are the kinds of things that we want to expand and use to build up this data set. Obviously, there's no law school, but I mean, thankfully, I kind of have a little bit of that covered. We have an incredible CS department, Leilani Gilpin, for example. She's working on model interpretability. This is a very cross-domain project that is impossible for me to achieve on my own. I can spot a few people in the crowd that are going to be helping with that as well. But yeah, UCSC feels like the right place for it. We have departments that talk to each other in ways that I haven't seen at many other institutions. Yeah.
Yeah, just to mention that, for example, the humanities division, this year is the year of technology for the Humanities Institute. And so, there's a number of efforts that are developing. There's a new effort in data and ethics, which is emerging, which is asking questions about, what is the ethical use of data? What is the ethics that surround the collection of data, and how do we know, right? So these are really, really important questions that are being taken up at multiple levels of inquiry, and it's really, really exciting. It's a really exciting time. Question?
Yeah, just a question from the audience. Suppose we could fabricate the brain using CMOS technology. do you think it's possible that we'd have the same power consumption as a biological brain?
If you were able to fabricate a brain in CMOS technology, all right, so I have to work with the assumption that that is true. That's a hard assumption. I can't do back of the envelope calculations on the fly. No, so I mean, what it would take to answer that question would basically be, all right, what's the energy access of a CMOS technology that is able to fabricate the brain? Do I have enough interconnectivity between every neuron? What's the cost of every single signal that's going into an individual node? Give me like 48 hours and I'll give you an answer.
Or you could just ask
ChatGPT.
ChatGPT.
As a large language model, I am unable to.
Okay, please.
You covered a lot of ground over the whole piece, but to go back to the middle part when you were talking a little bit about the medical application,
Yeah.
how did the research on epilepsy come up, and is that in collaboration with like a hospital, or has anyone been able to forecast a seizure?
Yeah, that was awesome because that was problem first, right? One of my good friends at the University of Sydney, a professor there, Omid Kaveh, he came to me and said, our forecasting models suck. How do we do better? And we just talked for ages. There were a lot of meals involved, and we back and forthed a lot. And then ultimately we landed on this idea. Forecasting seizures has been done, not in that specific way. In general, the forecasting models that succeeded were done on individual patients where your forecaster did not have to generalize at all. If you had to train a forecasting model on a large number of patients and ensure that you were able to get a good performance on all of them with one model, then that has not been done well. And even using individualized models in a hospital clinical setting, of course, there's a lot of challenges that come into that I've barely touched on. You also asked, was that in collaboration with a hospital? Yeah. Going a little bit more technical in that, we had pre-trained models on open source data sets to make sure that that was some sort of base model to work with. And then once we were fine-tuning, we used actually patient data from 10 patients with chronic epilepsy at the Royal Prince Alfred Hospital in Sydney. During COVID, I was stuck in Sydney, so it made sense to work close there. And yeah, that was it. That was who we had these pre-trained models adapt to. Yeah, it was the best performance that we'd seen on forecasting to date.
Can you just talk a little bit about what is inspiring your students? You seem to have a range of students with, or you must have a range of students with a range of interests, including undergraduate students. So how are you engaging with students?
You're asking me to be a lot more self-aware than I am.
You should be asking them. You're out there.
I think that they see that I'm excited. They see that I like my work. They see that I believe in my work. They see when I don't believe in my work as well. And believe me, there's many instances where I'm working on a problem. I'm just thinking, why the hell am I doing this? When that happens, yeah, you pivot. And right now I feel like focusing a lot more on the broader implications of AI is a huge, huge part of that. While I was a doomer during that flip-flopping phase, I got very jaded. I think a lot of us were jaded during the 2 years of lockdown, especially in Australia, where we were stuck inside for a hell of a long time. That had me very jaded about my work. I wasn't sure if what I was doing was the right thing. But then when you come up with opportunities, when you see that we actually have a bit of power to build something that could help people that need it, all right, maybe I should be building better AI, making it more decentralized, making it more power efficient, making it more individualized. That makes sense. And then I got excited again, and the students follow suit. They see that, he's doing something that he likes. Maybe I could like that as well. I'm not sure. Maybe excitement is contagious.
Are they more inspired by the applications, or are they more inspired by the technology?
Yeah, that's a really deep question. I would say it's student specific. I have not observed any trends. Some students come in with a very clear idea of what they want out of life, what they want to achieve. Some students like the technology. They were very fascinated in neuroscience, but ultimately they wanted to go into something more applied. And you know, neuroscience is a cutthroat field. It's tough to get jobs out there if you're not contributing to a company's bottom line. And so they went into engineering and they thought, damn, that's an opportunity that I can marry the two, or marry the 700 that I went over. And so no, I think that it's that. They realize that there's so much more to engineering than, I guess, what meets the eye. And this is a great field. Neuromorphic engineering threads so many things together. There's something for everyone.
Okay, one last question.
Thanks for the amazing talk, Jason. I wanted to kind of highlight what I see as like a tension maybe in the work, but I'm curious if you think that. So kind of looking at the last section, thinking about these kind of deep questions of authorship and ownership. You talk about Edmond de Boulamy, where the art collective really kind of leaned into this anthropomorphic notion of it's the AI who kind of made it, and that was kind of what got it to sell. It was the first time that an AI made art, and that's kind of wild. And there's this kind of tension that I think you talk about is it the AI that makes it, or is AI like a tool, like a fancy Photoshop that like humans are kind of using to make art? And so I'm just kind of wondering, thinking about the first kind of chunk of your work where you kind of are making these new class of AI systems that are changing over time and are taking data sequentially. Does that kind of lead us into a world of AI that is it still a tool? Is it kind of changing? Is it much more like the human brain? Does that change the way we think about technology as tools? I'm wondering what you think.
I think my mind is blown. Yeah, that's a lot to parse through. All right, so I think what we've observed in history, I've only got one example analogy to work with. Corporation law. The courts knew when to assign personhood to a company, to a corporation, when it made sense. Perhaps we'll reach a day when AI has sufficient agency, especially in the case where these models are evolving and human involvement is far more decoupled, as in with Edmond de Boulamy. No, there was someone training it, there was someone clicking run, there was a data set generated by humans, there were a bunch of conflicting human interests in that model. But what if agents start training each other? What if models start evolving? In that instance, maybe we'll see a day where AI, quote-unquote, personhood is prescribed. I have no idea. There's something that ChatGPT can't say. I have no idea. Someone needs to make ChatGPT humble.
On that note, thank you, and we'll turn back to Ray.
Thanks, Alex.
Thank you, Professor Ashragian and Dean Wolf, for joining us tonight at the lecture. And I hope all of you will join us on February 7th for our next Kraw lecture with UC Santa Cruz Professor Carol W. Greider. Professor Greider will be returning to the lecture series, and she is an eminent biologist and promoter of diversity in science who joined in the 2009 Nobel Prize in Physiology or Medicine for groundbreaking work in telomeres and also the discovery of telomerase. I think I got that right. Thank you all and good night.